So for this problem, we are given a 360-foot long submarine with a 33-foot diameter circular hull, and we're asked to solve for the weight of the submarine, and we're also told that it's in freshwater. And then just as a reminder, freshwater means that our specific weight of water is going to be 62.4 pounds per foot cubed, not the specific weight of salt water, which is 64 pounds per foot cubed. So again, keeping in mind, always got to check and make sure you know which specific weight you're going to use. So the way we're going to solve this problem is we're actually going to go back to the barge problem for a minute, right? So if you remember back to the barge problem, which hopefully you watched right before this, we had our nice rectangular barge and it was sitting in the water, right? And we had our Archimedes principle formula that the force of buoyancy was equal to the specific weight of water times the volume displaced, which came out to beam times length times draft, right? So that's taking a side-on view of the barge, right? So there's our length and there's our draft. And then the beam of the ship is kind of that into the page dimension that you kind of have to imagine. So now imagine we took a front-on view of that barge, right? So if we take a front-on view, we have that, we have our water line, and now we still have our draft going that way, but now the length of the ship is the into the page direction, and the beam is what we're looking at horizontally. So another way to think of that is that volume displaced is still beam times length times draft. But what we can do is if you look at this frontal area of the barge that's submerged, that area is equal to the beam times the draft. So we can rewrite the volume that's displaced as the area times the length. Now keep in mind, this only works if that area is uniform going all the way back, right? So if you look at our barge, you can imagine that the area at this point is the same as the area at this point is the same as the area at this point, because we said it was a perfect rectangle, right? So this strategy of calculating what we call a cross-sectional area that's going to be the same along the entire length can then be utilized for things that are other than just easy rectangles, right? Rectangles are easy, beam times draft. So now let's get to the problem we're actually trying to solve. We have a circular submarine hull, and for the sake of accuracy, we'll draw the sail on top of the submarine. And we're given the water line is halfway across the diameter of the submarine. We're told that this diameter is equal to 33 feet. So now what we can do is we still have this condition where we have a length of the submarine, which was given to us as 360 feet. And we can look at the front area and we can say, hey, if this submarine is a circle, then this area, right, the area of a circle is pi r squared. And since only half of it is submerged, the submerged area is then pi r squared over 2. And therefore, using this same equation for the submerged volume being equal to the area times the length, that then gives us pi r squared times length all over 2. So this is a really powerful way to approach these problems because it allows you to use very very odd geometries, right? So when we were doing our boxy barges and it was just, oh, length times width times height, right? Well, now we can say, hey, we have a submarine hull that's a perfect cylinder. There's times where you can approximate that, hey, a destroyer kind of looks like a triangle to a certain point. and then it kind of sticks up from there and kind of has a bridge and stuff. But hey, if the water line is right there, the submerged, this is a front view of a DDG. Well, it kind of looks like it's this triangular area under the water. So if we wanted the displaced volume, area times length, and then area of a triangle is just simple 1/2 base times height. And then you can do your geometry to figure out the base and the height of that triangle. So again, keep in mind this strategy of converting your displaced volume to being an area times a length only works if it's a uniform area down the length of the ship, which for this class is generally going to be a pretty good assumption. So let's go ahead and finish the problem, right? So we know this is Archimedes' principle. We know it's a floating object. If we want the weight of the submarine, it's going to be equal to the force of buoyancy acting on it because it's in static equilibrium. And because of Archimedes' principle, we know that that's equal to the specific weight of water times the volume displaced. We know that it's sitting in fresh water this time, so we'll label that FW for freshwater. And we know that that displaced volume can be represented by pi r squared L over 2. So in the end, we have specific weight of fresh water times pi r squared L over 2. Now the last thing we need to catch is, hey, they gave us the diameter of the submarine to start with. So let's go ahead, diameter, or radius is diameter divided by 2. So that gives us 16.5 feet for the radius. So we'll go ahead and plug everything in. So we have 62.4 pounds per foot cubed times pi over 2 times 16.5 feet squared times 360 feet. And then traditionally for ships, you want to express your weights in long tons. If you leave it in pounds, you get a very, very, very large number. So we'll go ahead and this feet and this feet squared will cancel out with the feet cubed. So then if we want to remove the pounds, we can say that 2,240 pounds is equal to 1 long ton. So we go through and calculate that all out, and we get that the weight of the submarine is 4,289 long tons. Okay, so now let's take a look at how well our approximations work. So if you look at the picture, that's a Los Angeles class fast attack submarine returning from deployment. So if you look it up on Wikipedia, the actual weight of a surfaced Los Angeles is about 6,000 long tons. Well, so why the discrepancy? Why didn't our problem work? So one, the submarines are not actually uniform going all the way back, right? If you imagine looking at the front of the submarine, it's got the sonar dome where everything comes super narrow. So that's one assumption we made that's not true. And then also, no reason you should know this, submarines do not sit half in the water when they're surfaced. So if you look at an actual submarine, you would see that the water line is probably more like there. So how does that affect our answer? Well, if the submarine were more submerged, that would cause this area that's underwater to go up. Therefore, the volume of submerged would go up. So the volume of water displaced would go up. And if the volume of water displaced goes up, that would cause the force of buoyancy to go up, which would mean our submarine is heavier, which checks with what we would have expected to have happen. So that just a way you can kind of think about these problems. Like you can go ahead and if you get answers, start thinking about, does this match with reality? And if not, why not? And if you go think about those assumptions, that's a really useful skill that you can get out of this class. So again, big points to take away from this problem are if you have a uniform cross-sectional area, your displaced volume can just be equal to that area times the length of the ship that you're looking at.